Hey everyone, and welcome. Today we're going to tackle a really cool concept, something that's at the very heart of computer science, the longest common subsequence.
You know, have you ever stopped to wonder how a tool like Git just knows the exact lines you changed in your code? Or how a plagiarism checker can spot that one matching sentence in a sea of text? Well, the magic behind a lot of that is the very algorithm we're going to explore right now.
Alright, so before we can find the longest common subsequence, we have to get crystal clear on what a subsequence actually is. It sounds simple, but trust me, getting this distinction right is super important.
Okay, so a subsequence is just a bunch of characters you pull from a string, but, and this is the big rule, they have to stay in their original order. Think about it like a grocery list. If your list is apples, bread, carrots, eggs, then apples, carrots, eggs is a totally valid subsequence. See? We skipped bread, but the other items are still in the order they were on the original list.
Now, this is where people sometimes get tripped up. It's easy to confuse a subsequence with a substring. A substring has to be one continuous, unbroken block of characters, like ABC right out of ABCDE. But a subsequence, like you see here, can have gaps. We can pluck out A, then C, then E from ABCDE. And as long as we keep them in that ACE order, it's a perfectly good subsequence. This difference is everything for what we're about to do.
Alright, so if I asked you to find the longest common subsequence, what's the first thing that comes to mind? Probably just listing out all the possibilities, right? Well, that's the brute force method, and let me tell you, it's a trap. Let's see why.
So this naive approach, it's like trying to find the best route through a city by literally driving down every single possible street. You'd generate every single subsequence from the first string, and for each one you'd check if it exists in the second. Yeah, you'd get the right answer, eventually, but you'd be recalculating the same small comparisons over and over and over again, and that is what makes it so slow.
And here's what that looks like in computer science terms. The time complexity is O of 2n, which is exponential. Now, what does that really mean? It means for every single letter you add to your string, the amount of work pretty much doubles. For a tiny string, okay, maybe it's fine. But for a paragraph, a whole document, forget about it. This approach is completely, totally impossible.
Okay, so if brute force is a dead end, what's the smart way out? Well, it's this incredibly powerful technique called dynamic programming. The best way to think about it is like we're creating a map that will help us find the answer without getting lost and redoing all our work.
All right, let's make this real. For the next few minutes, we are going to solve this exact problem. Our first string, x, is AGGTAB, and our second, y, is GXTXAYB. Our mission, find the longest sequence of characters that shows up in both of them in the same order.
So, to build this map, we're going to fill out a grid, and we only need two simple rules to do it. Rule number 1, if the characters we're looking at match, we've just found another piece of our common sequence. So we just look at the cell diagonally up and to the left and add 1 to whatever number is there. Rule number 2, if the characters don't match, well, no new match was found, so we just carry forward the best result we've seen so far. That means we take the bigger number from either the cell directly above us or the cell right to our left.
All right, here we go. Here's our grid, our map. We've put one string across the top and the other one down the side. Now, every single cell in this table is going to store an answer to a tiny subproblem. It's going to tell us the length of the longest common subsequence for just the parts of the strings we've seen up to that point.
Okay, let's start filling this thing in. We'll start by comparing the first A from our first string with the G from the second. Do they match? Nope. So we use rule 2. We look at the cell above and the cell to the left, and we just take the max value. In this case, they're both 0, so we put a 0. All we're saying here is, hey, no new match found, so let's just carry over the best we had so far. All right, let's fast forward a little to a more interesting spot. Here, we're comparing the G from the first string with the G from the second. Hey, we've got a match. This is where rule 1 kicks in. We look diagonally up and to the left, we see that 0, and we add 1. Boom, this 1 in our table now means we've officially found a common subsequence that's 1 character long.
And that's it. We just keep following those two simple rules, methodically filling out the entire table, one cell at a time, and when it's all filled out, we just look at the very bottom right corner. That number right there, that's our answer. In our case, it's a 4. This means the length of the longest common subsequence is 4.
Okay, that's great. The number 4 tells us the length, but what is the actual sequence?
Well, the cool part is we don't have to do any more math. The answer is already hidden inside the map we just built. We just have to trace our steps backward.
And guess what? The rules for going backward are just as simple. We start in that bottom right corner. If the characters for that row and column match, that character is part of our answer. We add it to our list, and then we move diagonally up and to the left. If they don't match, we just follow the path of the bigger number. We move to whichever cell gave us our value, either the one above or the one to the left. So let's do it. We're at the bottom right, the cell with the 4. The characters are B and B. They match. Awesome. So B is the last letter of our answer. We add it to our sequence and move diagonally up left. Now we're looking at A and Y. No match. So we move to the cell with the bigger value, in this case to the left. Okay, next up, A and A. It's a match, so A is the next letter. We add it to our sequence, move diagonally again, and we just keep doing this all the way to the top. We build the sequence backward, and when we're done, we just flip it around to get our final answer, GTAB. Now, I know this might feel like a fun little abstract puzzle, but this exact logic, it's the engine running behind some of the most important software you and I use every single day. Let's look at a few examples.
So in bioinformatics, scientists use this to align massive DNA sequences. In software version control tools like Git, this is what powers the diff command. And of course, it's a huge part of plagiarism detection and even data compression. In every one of these cases, it's all about one thing: efficiently finding what's the same between two giant chunks of data.
And why is efficiency such a big deal? Well, get this. The human genome has about 3,000 billion base pairs. Trying to compare that to another sequence using that naive brute force method, you just can't. It is not an option. An efficient algorithm like the one we just walked through is literally what makes modern genomics possible.
So let's sum it all up. That naive approach is basically unusable because of its exponential time. But our dynamic programming method, it brings the time way down to O of m times n, where m and n are just the lengths of our strings. That's a game-changing improvement. And as you can see here, there are even some clever tricks to optimize the memory you use, which is super important when you're dealing with massive data sets. Okay, for anyone studying for a technical interview or a computer science exam, listen up, because this slide is pure gold. If you ever see a problem that asks you to find the longest sequence or the minimum number of edits or the maximum profit from a bunch of choices, a little alarm bell should go off in your head that says dynamic programming. It's a super common pattern. So if there's just one thing you remember from all this, let it be this mental picture. Solving the longest common subsequence problem is a two-step dance. First, you build the table, your map, to find out the length of the answer. Then you just walk backwards through that same map to figure out what the sequence actually is.
You know, this whole idea, taking a massive, intimidating problem and breaking it down into tiny, solvable pieces, and then building the solution up from there, it's one of the most powerful concepts in all of computer science. And it kind of makes you wonder, right? What other huge problems, maybe even ones in your own life, could be solved by just patiently mapping them out one small logical step at a time?